Alright, so we're going to introduce fractional exponents today and talk about how they work, and also solving radical equations as we go through this. So we're going to start with the definition. So b to the 1 over n power is the nth root of b. So it's a different way to write a radical with now a fractional exponent. So an example, 8 to the 1/3 is asking for the cube root of 8, which is 2. And why is that true? Well, 2 to the 3rd times 1/3 power, I multiply those powers. 3 times a third is 1, and that gives me 2. So I can see and simplify these if I look at powers that aren't necessarily ones where the numerator is 1. So if I look at 4 to the 3 halves, that's 4 to the 3 times a half, which is 4 to the 3rd times a half power, raised to the half power. And 4 to the 3rd is 64, and then the half power asks for the square of 64, which gives me 8. I could do it differently if I wanted to. So let's say I did it the other way, where it's 4 squared to the half power times to the 3rd power, and then I can combine my fractional exponents. 1/2 times 2 is 1, 3 times 1 is 3, so 2 to the 3rd power gives me 8. So different ways to go about doing this. Sometimes it's going to be simpler when we look at rationalizing the denominator, or taking a nth root where n is not something easy like a square root. Alright, so again, we got the same answer as we know we should have. So what about our negative value? So if we look at this, remember our negative exponents means the reciprocal of what we have going. So we can break up that fraction in r to the -3 to the 1/4 power, which is 1 over r to the 3rd to the 1/4 power, which is asking for the 4th root of 1 over 3. So the same rules apply with negatives, where it becomes a reciprocal as we do this. Alright, we can also, what really helps us sometimes is rationalizing the denominator. So let's say we have a problem where we have this value. What we're looking for is we write it with our fractional exponents, which becomes a to the 4th over b to the 3rd, all to the 1/2 power, and then I distribute that exponent and multiply it out, and I get a squared on the top, and then I have to deal with the bottom. And I need to raise b to a power so that I get b to the 1st power. Well, I could just take the reciprocal of the 3 halves and get 2/3. So if I multiply everything by b to the 2/3, my denominator should simplify. So I get a squared, b to the 2/3, and then when I multiply the exponents on the bottom, I get b to the 1st power. So then I've rationalized the denominator, and it's a little bit easier to see what power I need to raise everything to make it work. We might also be asked to simplify something. So if I have a like base, in this case 3, my rules for exponent powers still apply, where if I'm multiplying the bases, I add the exponents. So like bases, I add those up. 3 to the 3rd plus 2/5, and I get a common denominator of 15, and I combine that for 3 to the 11/15. So again, it's the same rules we've had before, but we now have an additional thing we can use with these fractional exponents. Alright. What if we're solving radical equations? So let's look at a couple in terms of what that means. So if I have an equation that looks like this, it's the same process as we go through before. So I'm going to add 6 to both sides. And then I have this square root that I have to deal with. Well, my inverse operation for square root is squaring everything. So I'm going to get x plus 2 is 256, and I subtract 2, and I think x is 254. Well, I need to check this, and we'll see why in a minute. But if I plug in 254 again, I get 16 minus 6 is 10. It does check out, but it might not. So if we look at another problem, the 4th root of x plus 2 plus 4 equals 3. If I subtract my 4 from both sides, I get -1. Now we could stop right there, because I know that we've defined these even roots to be a principal root where we have a positive value. So just like the square root of 49 is plus or minus 7, but we define it to just be the positive. We'll see what happens as we plug through this. So if I bring everything to the 4th power, I get x is -1. If I check it, and -1 plus 2 is going to be 1, the 4th root of 1, we define to be 1. That's our principal root. So there's no way that I can get a -1 out. So we say this has no solution. So again, once we've restricted things to the principal root, so we have a function and not just a relation, we have some problems as we're trying to solve these equations. Let's look at the next one. It's the same idea. Alright, if I was to subtract 10 from both sides, I get the opposite of the square root of x plus 1 equals 2. Square everything, and I get x plus 1 equals 4. minus 1, x equals 3. But again, if I plug that back in, what's going to happen is I get 10 minus 2, which is not equal to 12. So what I again would need is the square root of 4 is plus or minus 2, but we've defined it to have a principal root of positive 2, which means the square root of 4 will not give us the negative 2 back, which means we can't get to 12. When we have something like this, we call it an extraneous solution. It's almost like an extra solution. It's not a solution per se because it violates the principal root, but we can solve for something. It just doesn't check with our original function equation. All right, what about something where I have radicals on two radicals that aren't connected? Now, what I can't do is just call it the square root of x minus 8 minus x, the whole thing. I can't undo that. I can't factor that out that way. But I can add the square root of x to both sides. And I get square root of x minus 8 equals x plus 2. And now I want to square everything. So if I square everything, I get x minus 8 on the left-hand side. And on the right-hand side, I got to FOIL it out. And I get this value. And I notice that the square root squared goes to x, and then I'm going to have 4 times square root of x plus 4. And why this is nice is my x's are going to go away. So I'm going to be left with 0 equals 4 root x plus 12. And I can factor that. I can divide by 4. I'm going to get x is the square root of square root of x is negative 3. And again, that violates my principal root. I can't have a negative value pop out. So this is going to have no solution because it violates the principal. We couldn't see that necessarily from before, but this is one way that we can go through this and solve these equations. And again, we need to be very careful that we check our values to see that this principal root idea isn't being violated.